Saxon's Trig, Lesson 83, is about simple probability, independent events, and replacement, starting on page 499. So simple probability, and you'll see that I already have something here, but I'm coming to that. I just wanted to go ahead and write that chart out rather than take the time to do it on the video. So hold that thought, it has nothing to do with part A. Simple probability is creating a fraction which the numerator part says whatever answers the question, and the denominator part says however many the total is of something. So probability is based on the study of outcomes that have an equal chance of occurring. And I've just told you that they're in fractions. So it is customary to call activities such as flipping coins, rolling dice, blindly selecting cards from a deck, or drawing marbles from urn experiments, and to call the individual results the outcomes of those experiments. And then that set of outcomes, so whatever the list of the outcomes are, we would call those the sample space for the experiment. So like if the answers were 1, 5, 9, 6, and 10, then if I said I want to talk about the subset of the second outcome and the third outcome, then I'm talking about using the 5 and the 9, and that would be the subset that they're talking about there of events. So the event would be whatever caused me to get the 5 as the result, and whatever caused me to get the 9 as the result, that would be the event. So the probability of a particular event happening. So in this list, if I said, what is the probability I get a 6 when I have done something or other that got me these results? Well, there's only 1 6 in my list. So my probability would be 1 out of how many? 1, 2, 3, 4, 5 choices that I had. So the probability of getting a 6 is 1/5. Same probability to get a 10 or a 1 or a 5 or a 9. All right, so then they shift and they say, all right, let's talk about the specifics of, because in the list they said flipping coins, rolling dice, blindly selecting cards from a deck, and then drawing marbles from an urn. Out of that list, the only thing I will caution is, it doesn't happen so much anymore, but when I first started teaching, students were very nervous about card problems because their parents didn't want them messing with cards in any way. As long as you understand the basics in the cards, you can answer these questions without it leading to gambling or anything else. So just in case, there are 4 different sets in cards. There is a spade, heart, club, and what's the other one? Spade, heart, club. It'll hit me in just a second. 2 of them are black, 2 of them are red. Heart is red, spade and club are black in color, and the other one is the red. Again, it's going to hit me. Within each of these sets, there is a king, a queen, a jack, and then the numbers 10 down through 1. And that's really all you need to know. As soon as I can remember this name here. Spade, heart, club, diamond. Haha. All right. And it's also red. All right. And then each one of these sets has a king, a queen, a jack, and then 10 all the way down through. Not 1. 1 is the jack. 2. Okay, now we're back on track. Okay, that's all you really need to know to answer any kind of questions that they would have about cards. So if you don't know anything about cards, obviously jotting that down will be very helpful for you. But the first thing they talked about here was flipping coins. So if I flip a coin, it's either going to have heads or tails. Those are the only 2 options. And then if I'm asking for the probability of getting heads, you're going to see that P for probability. In the parenthesis is what they're asking you to find. How many heads are there on a coin? 1. How many sides are on a coin? 2. So the probability is 1/2. Now, if we talk about dice, you have the options 1, 2, 3, 4, 5, and 6 on a die. And if I asked for the probability of getting a 5, that would be 1 5 out of 6 numbers, 1/6. If I asked for the probability of a number greater than 4, how many numbers greater than 4 are there? Not including 4, because there's no equal. 5 and 6, so that's 2 out of 6, and that will reduce to a probability of 1/3. Now that you have those basics, this is where my chart comes in. Now, some students have the quick ability to add these in their head and kind of either jot the count on the side and then just put it in their answer. But if you want to see what the combination of numbers are for rolling 2 die, this was the 1 through 6 from one die, this is the 1 through 6 from the other. This is the result of the sum of a 1 and a 1 coming up, that's a 2. A 1 and a 2 coming up is a 3. A 2 and a 4 coming up is a 6, and so on. So you'll see why when we do example 1, why this is possibly a helpful chart to have. 2 fair dice are rolled. And if they don't clarify fair dice, it could be a trick die, and obviously that's going to cause a problem and you're not going to get this chart of results. So they have to clarify 2 fair dice are rolled. What is the probability of getting in part A 7 and in part B a number greater than 8? So for A, it said a 7. How many results of 7 are there? And it's nice that they're catty corner. So 1, 2, 3, 4, 5, 6 results out of, and 6 by 6, there are 36 results here, and that's going to reduce down to 1/6. And then in B, it asks for a number greater than 8. So let's see, not including 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 results out of the same 36. Reducing down by 2 is going to be 5/18. And that doesn't reduce any further. So those are my answers for A and B. They go through a lot more explanation there. Further division probability. Okay, we're not going to worry about any of that. Moving on to part B is independent events. And so the independent events are what happens when I take a coin and I toss it 3 times rather than just 1 time. So if I want to know the probability of getting a heads all 3 times, I need a way to do that without drawing a chart. So let me show you the chart and then you'll see why you don't want to draw it. So if I take a coin and I toss it, I can either have it come up heads or tails. After the first heads, when I toss the second time, so if it came up heads, here's my second toss. I can get a heads or a tails off of that. If it came up tails the first time, the second time I still can get a heads or tails. So far to get heads and heads, I'm using this trail of it. Third time I toss, I can get heads or tails, heads or tails, heads or tails, and finally the heads or tails. So there's only one chance of getting all 3 heads out of how many combinations were there? Well, if I just count the end results, I know how many possibilities there were. 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's not too horrible for a small one. However, if I tossed it 10 times, I certainly don't want to be doing a chart for 10 times. Can I find a shortcut? Yes. So what is the probability in one toss that I get heads? A half. What's the probability I get heads the second time I toss? A half. And the third time I toss? A half. How should I combine those numbers? Multiply them, just like the probabilities from before when we were doing the lines and filling them in, or the circle probability, that sort of thing. So now you multiply those together. 1 times 1 times 1 is 1. 2 times 2 is 4 times 2 is 8. Oh, beautiful. I don't have to do charts. I can do the individual probabilities and then multiply them together. So these are each independent tosses, because what this one ends up giving me does not affect what the second one will give me. That's why they're independent. Now, let's look at example 2. A fair coin is tossed 3 times. What is the probability it comes up heads every time? Oh, I've already done that one. Beautiful. Example 3. A fair coin is tossed 4 times and it comes up heads each time. So we're looking for heads, 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 and heads. And then it says, What is the probability it will come up heads on the next toss? Ooh, tricky, because I only care about the next toss. Doesn't matter how many times it came up heads before. There is 1/2 of a chance it's going to be heads the next time I toss it. So I don't even need to do the multiply there. So make sure you read the question carefully to figure out what they're asking for. Part C deals with making a replacement. So this is more where you deal with your urn containing marbles or something else, or a bag containing something. Example 4. An urn contains 2 black marbles and 2 white marbles. A marble is drawn at random and put back in. Okay, so these are in a bag there you go, if you need a visual for that. Okay, then a second marble is randomly drawn. Question A says, what is the probability that both marbles are black? Okay, so they're independent draws. So how many blacks did I have to choose from? 2. How many marbles were there? 4. And then I put it back. So how many blacks? Still 2 out of 4. And each of those reduced down to 1/2. So it's 1/2 times 1/2 when I put independent events together. So the probability it comes up black 2 times is that 1/4. Part B says, if the first marble is not replaced before the second marble is drawn, what is the probability that both marbles are black? First draw is still that 2/4, but now the black marble is sitting out here, so I only have 1 black marble left inside. How many black marbles do I have to choose from? Just the 1. Now how many marbles are in there? 3. So that's going to reduce to that 1/2 times 1/3, which is basically a 1/6. So it's much less of a chance there when I don't replace. Last example deals with cards, example 5. 2 cards are drawn from a 52 card deck. Oh, I guess you should know there are, well, you could figure that out. If you counted how many of those there were in each one, and there are 4 of them, then you know that you have 52 cards total. So I guess that information was sufficient, but it is nice to know there are 52 cards in a deck. You're going to draw 2 without replacing. What is the probability that the first one is red and the second one is black? All right, so we said before that I had 2 different sets that were red, so that basically 1/2 of the deck is red. 1/2 of 52 is 26 out of 52 cards. But I left, no, wait a minute, just a second. Probability. First one is red, yes, and the second one is black. I'm not replacing. So at this point, I have a red sitting out here, which has reduced the number of reds down to 25 reds in there. But for blacks, I still have 1/2 the deck, that's 26. So how many do I have for black to choose from? 26. But how many cards, were left to be choosing from? Well, I lost 1, so I'm down to 51, or that's what I get when I would add 25 with 26. Independent events multiply together. See if you can reduce anything down. Well, the 26 out of 52 is definitely going to be 1/2. You know what? I might just do that on the calculator and not worry about it and reduce it. It should come out to 13 over 51. Okay, let me keep playing here. 2 goes in here 13 times. If I make this 1/2, no, hang on. 2. 26 times 2. Yes, 52. Why am I not getting 2 times 51? 26 out of 52, 26 out of 51. Did they reduce it incorrectly, or am I? Okay, I'm gonna pause it while I figure this out. I got partway through the calculations when it hit me what I had done wrong. I knew it had to be something simple. This I reduced to 1/2, but I had already reduced this with this, and that's what I failed to take into account. So the 2 went into the 26 and left me the 13. The 2 didn't exist. That is 13 over 51, very simply. I didn't think the book would have an error there. I just needed to figure out where I had made my silly calculation. Now you can see it too.